So installing a battery charger is a pretty basic thing. Here, don't get fooled, black is not negative, it is actually positive. So peel that back with the battery charger unplugged. So first what we can do is measure the voltage. Now I've already charged this battery. Now I've been playing with the lights in the chute. We have got 12.04. Let's apply the black. So kind of a sensible question is why we would bother attaching the red before the black. And I think most people know that the black, negative, is bonded to the frame, or it's connected to the frame solidly. So they're at the same potential. Whereas the red is the energized component in the whole unit. So if you were to attach the black first and then you fumble the red and you drop it on the frame or any part that's considered, ground, even though it's not hooked up to ground, you'll get a short circuit. Whereas if you hook up the red first, like I did here, then you don't run the risk of a short circuit if you drop the black alligator clip onto the frame or anything. The charging process will begin, but at least you're not short circuiting where you can cause sparks and other undesirable effects like that, especially when boosting a vehicle or using an older style battery charger. Then we can plug in the charger. We plug this little battery tender Junior 800. We select lead acid, which is already selected, and then this amber light indicates the battery is charging. Do another voltage measurement. We'll actually see the battery charger in action as we're at 12.22 volts, 12.23, 12.24. All right, here we are 2 hours after we last left. Let's check the voltage on this battery. The charger still indicates charging, which is a little bit odd, but it is a big battery. So 14.35. So it's just floating the battery for some time, I suppose. Now one interesting piece here is to see what current it's actually flowing. So I can hear the battery. Oh, it sounds like boiling. So now we've got 0. Put that on there. We've got 0.6. We've got 0.6 of an amp, and here the standard charging current is 1.4 amps. So if we kept the clamp meter on this at 0.6, we should eventually just drop down and down and down until the charger thinks it's done. There's definitely somebody out there that's going to say, hey, how much does this LED light draw? Put our clamp meter on there. Here we've got 0. Turn on the... So we've got 0.4 amps, 0.5 amps on the LED. Now if we do the chute, we've got a good 4 amps. Alright, battery charger says it's done. Let's measure the current that's flowing again. And lo and behold, it's 0. Let's check the final voltage. We have 13.15. It's kind of holding there. But I can hear the charger acting, so we take that off, remove this. 13.08, 13.07, 13.06, and then that's going to find its happy place. Since so many people love these snowblowers and they very much love not cranking them because they have electric start, and they have an electric start that you don't have to plug into a 120 volt outlet, which to me is a pain in the butt. Let's document, the starting current, the starting voltage, and the ignition of a startup of a YT624EJ. So here I've got the instruments installed. I've got a current clamp installed off the battery, and as well as a voltage probe. These are going down to the oscilloscope USB, which is hooked up to the computer here. So I'm going to go ahead, give this a start. I've got a trigger set for 11.4 volts. So as soon as the start is given, the voltage will drop and the waveform will record. So we'll check out the data and see what we've got. So as I said before, I'm an engineer, and specifically electrical engineer.
I think it's always important to look at the drawings before we start taking any measurements to understand what we're actually measuring. I'll just rattle off a few of the aspects of these standard electrical drawings. So number one, we see here we've got the negative terminal of the battery connected to the frame. So anywhere where you see this symbol in the entire drawing means that that wire, that component is hooked up to the frame. Here we have the very obvious symbol for a battery showing that the negative, again, is hooked up to the frame. And the positive comes out and goes to this number 9 starter relay. Very standard component on all kinds of cars and stuff like that, and snow blowers and other stuff. So we see as well that this item 11, so we've got number 9 crossed off, starter relay. We see here that number 11 is a starter motor. The starter motor is what starts the engine. So it's got one wire hooked up to, we're going to call it ground, but it's not ground, but everyone likes to call it ground. Let's call it ground. So we've got the motor here. Now, the other wire of the motor comes to this red. It says that it's red, R for red, and it goes again to the starter relay. Now, if we go between the battery positive and the motor, the only thing we've got there is this switch. Well, actually, it's a contactor. Well, actually, it's a relay because it's small. So if we see when does this paddle get pulled in, this paddle is going to get pulled in when this coil becomes energized. And so the next question is, well, when's the coil going to become energized? Well, if we look here how this relay works, the red wire goes out through number 10. It's a fuse. That's for example if you install your battery backwards. How do I know that? Because I've done it. So the red wire comes out through this connector here, and the red goes out, and if we look almost exclusively where it goes, primarily to this location here, red, and then red goes to these pins, and I just happen to know that when the key is turned on in the full position, the wire comes RN back to, now I know this because I did a little bit of pre-work. So RN comes back to, I believe, which is this terminal, and then you have the GNW. I'm going to make a jump here. The GNW is hooked up to white, which is a terrible name for a bonding conductor, but anyway, they've decided to go with white. So white, and then GNW comes down there. Now, I'm not totally sure why they've decided to switch the white. So if you follow the white back up through here, the GNW is like a switched earth, and it comes down here, but they're joined here anyway. So I'm not going to concern myself with that at the moment. So GNW is almost always present in the starter relay, and then RN will become present when you turn this key. So this function here is literally when you turn the key, this is going to happen. So then this coil is going to become energized. The moment the coil comes energized, this contact is going to drive in and energize the motor. When you release the key, the motor stops turning. So when the motor starts turning, then our favorite magneto, small generator, item 3, it's going to begin turning as well. When it begins turning, it's going to give us some voltage. And when it gives us voltage, it's going to apply it across this transformer, which is going to elevate it to our friend, the spark plug. When the spark plug begins to fire, the bootstrapping process is complete, and the engine can now start firing and turning on its own volition, which we're going to see in the waveforms. So item 2 is what they call the TCI unit, and then item 3 is the TCI magneto. So upon further inspection, even though it's called the TCI magneto, the magneto will go along this wire here into the item 4, which looks pretty innocuous, but it is the rectifier regulator. So if anybody's interested, really interested, I can do the waveforms of that, but I've done similar in the past on snowmobiles. So the rectifier regulator will take that AC which comes out of this magneto, convert it to DC, and then apply that DC voltage on the red, which will charge the battery. Whereas this TCI magneto will somehow transmit voltage into the coil assembly to generate probably our 10,000 to 15,000 volts for application across the spark plug. And also number 12 is our battery, like I've indicated before. Number 8 is that small motor that controls the direction of the chute. It's pretty direct what's going on here, but you know it'll either turn one way or the other based on the polarity, based on this switch. So this switch will take in, you know, the RNI, which is the switched red, and then it'll just switch it from positive to negative to give to this motor. Then we've got the light, and we'll notice the light is also on RNI, so when you turn the key on, it'll turn on. So the key on the first position. So the RNI is doing a few things here, and it's switched a couple different ways. So the RNI would be like the accessory one, whereas the RN would be when you want to actually start, and the key's on in the full position to start the motor. So these colors may be defined elsewhere in the book, but we don't really have time to go and pull all those. So one last observation on this drawing here is that the white here that goes to the TCI unit, that's not the same white as all the others. So if you notice, there's no dot here, whereas down here there's a dot to show you the whites are joined. So this white is an independent white, goes all the way to this switch, and it comes from GNW. Now GNW is actually hooked up to white, which is hooked up to so-called ground. The point being here is that this TCI unit will not be connected, the high end of it will not be connected to that ground until you've turned the key on and then connected the top end of it. I'm not super sure as to its functioning and why you would want to apply the bonding reference up here. So I don't really know of its design, but just keep in mind that just because it says W doesn't mean it's directly connected to the other W. So you need to have these dots, which, you know, you see the dot that's in there? That tells you that wires are connected, similar to here, to the red. But sometimes it's not as obvious, especially if there's 4 wires going into it. Alright, so for anyone who's still around, still watching, I'd like to go through some of these waveforms. Here I've plotted the starting sequence from the starter voltage and current. The pre-event time, so this is what I'd consider the event time, typically we call it trigger. We see the battery voltage is up here, and it is 12.55 volts. So the battery is fully charged, nearly fully charged, and down here we've got current on there, and actually I see that the current is 0. So that's what we would expect. Once the key gets turned to the start position and the starter motor starts, we see that our voltage drops to about 10.25 volts, which is very typical during a start. If this voltage were to drop down to 3, 4, 6 volts, that means your battery's toast. So 10 volts is quite good, and the reason that the voltage drops is because the current goes up to start the motor and turn the engine over. So we see here that the moment that the voltage goes down, the current goes up, and we've got about 140 amps there flowing at that moment in time. Now, if you see the pre-event current, you know, it's very tight bound here, whereas there's a lot of noise that's in there. Frankly, I don't know why the noise is there. It's quite noisy. So if we do 140 amps times 10 volts, we've got about 1.4 kilowatts of energy during this time. So we see then that the engine cranks for about 0.2 seconds. And then finally, the voltage goes back up to just underneath 12 volts, and then the current goes way down. So the engine starts spinning on its own and not needing the battery anymore to spin. So probably the engine speeds exceeded the clutch speed, if there's one, or the little pawl that came out or what have you. So after that, it looks like the no-load starter current is maybe, I don't know, 20 amps, as can be seen down here. And with the voltage going back up, when the key is then released at time, you know, 0.61 approximately, the key is released, the current goes back down to 0, and the voltage now is probably being pulled up by the charger here at this point, by the rectifier. So to me, it's pretty cut and dry starting sequence. It takes about 0.2, 0.3 seconds for the engine to spin up, based on my observations here. If I go to the other waveform, I've now plotted the starter current, which is here in red or green because I'm colorblind, and then I've plotted the ignition pulses with it. So we see that as soon as the starter current goes from 0 up to its 120, 130 amps, we get our first pulse only 0.05 seconds later approximately. It's really not that long. And then the engine clearly starts turning. We got our second pulse, third, fourth pulse, and then the engine takes off on its own. So I think it's kind of neat to see, how long it takes for the engine to start firing on its own and turning the shaft on its own volition. And it's at that same moment that the amps to the starter drop off, go down to zero at this point here when when I finally release the key. So here I held the key for about 0.5 seconds roughly. If someone has a really quick hand, they can probably release the key a lot faster than that. Here as well, the key was held for the 0.5, 0.6 seconds, but really you could let go of the key after 0.3, but no one likes starting it and having it drop out. Now, I've also done two things here, is that I've plotted the ignition pulses on their own when the engine's at idle. And the purpose of doing that is that you can then take a calculation of how long it takes to generate a certain number of pulses and figure out how fast the engine's going. So I've done that. So it took us for 10 pulses, our first pulse time was this, our last pulse time was this. Take the difference and do a simple division. You end up with how many pulses per second, and then how many pulses per minute, and then you calculate RPM. So my idle RPM is 2676 revolutions per minute, and the spec is 2300 plus or minus 100. So max spec on RPM is 2400, and I'm at 2676. I'm not in a rush to go fix this, because frankly I don't feel like it, and I got to tend to the children. And apparently I have to take the gas tank off, which I'm not in the mood to do right now, but maybe later if people are interested we could try to adjust RPM. To me it's fine. The other one I've done is the full speed ignition pulses. So here I just put the throttle to fast, or to max. Again, took the time of this pulse, took the time of this pulse, took the division, and then have it this way here. So 15 pulses, we have this much time. Calculate 4123 RPM, and the spec is 3800 RPM, or a maximum of 3850. So we're over here, but we're not under load either. So, to me, I'm really not concerned about this, and I wouldn't go out of my way to do it, even being as anal as I am. Now, the question is, well, what does this signal even mean? Well, this signal here comes from a Handtech HT25 capacitive probe that's installed on the high voltage lead of the spark plug. So it's capacitively transmitting voltage to the input of the oscilloscope. It's a very low amount of volts, but it tells you when the voltage is going high on that particular thing. So why are the pulses uneven? No particular reason. I've not gone and studied this extensively. The point is that the plug is very, very likely firing at all these moments right here that you could see. So hopefully this is useful to people. I know I went through it fast, but the video is already quite lengthy, and I think these are really neat waveforms, and I've done some on my motorcycle. I've done some on snowmobiles, capture the pulses, the rectifier regulator. I think they're always neat, and if anyone wants anything in particular, I'd probably be willing to do it if it could bring value to someone. Okay, thanks, bye.